In lesson 6.1, we'll be doing exponential functions and their graph. Here are the objectives. Determine attributes of exponential functions, graph exponential functions, identify and evaluate piecewise defined functions, and solve elementary exponential equations. Now, for some background, and again, you can always pause and read this yourself. We have in the past looked at expressions, equations in which variables had exponents, whether they were whole numbers or whether they were fractions, or in rational functions that are not polynomials where the exponents were negative on the variable. Now, as we look at exponential functions, we're going to see the general form is we have a base now that's raised to a variable. So the exponent itself is the variable. So I'll give you a few moments, pause, and read what is mentioned here. So in summary, we're looking at our base here, A, has to be greater than 0. That is, you can't have negative values. And A, that base, cannot equal 1. Because if it were, then all of the powers of 1 always end up being 1. And the other thing to remember that A to the 0 power, any base except 0 itself, to the 0 power is defined as 1. All right, let's go on. And completing, we want to look at what transcendental functions are. We have the regular algebra, which defines our regular kinds of things, polynomial functions, root functions, and rational functions, while logarithmic, trigonomic, and hyperbolic functions that will be studied a little bit here are examples of transcendental functions. Background. Going on to this next slide here, this is table 1, and I've put it into a t-chart for the function they're giving us. And just to note sort of the trend of what's going on. Now, if you have a fraction that is to an exponential power that is variable, notice what happens. If x is a -2, this becomes a 9. If it's a -1, this becomes a 3. If it's 0, anything to the 0 power is 1. Now, 1/3 to the first power is 1/3. 1/3 to the second power is 1/9. I've added 1 here. 1/3 to the third power is 1/27. So notice, if you have a fraction, that is something greater than 0, but less than 1, your values for negative are high. As the negative gets closer to 0, the values get smaller, and then on the other side, they get smaller still. Now, we're going to put this on a graph in a moment. Again, you can sketch what you want here. Now, here, this was 1/3. Again, now we have a number that x is greater than 1. So 1.1, 1.2, greater than 1. We're using 2 as a nice even value. So using the same x coordinates, notice what happens. When the x values are negative and they start to approach 0, the fractional values get larger. And then, of course, once it reaches 2 to the 0 power is 1, Now 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. Now, basically what I want you then to note as we look at the graphs of these, what is going on. I'll leave the t-charts up as we look at the graph. So the fractional base, as we look at x, negative values approaching 0, we say y is decreasing and then going up, and it forms this basic shape. Now, as we continue to look at the next, 2 to the x power, whereas x is increasing, y is increasing as well. Now, some vocabulary from the past, as we see the blue curve gets closer and closer on the first quadrant here to the x-axis, but actually never reaches the x-axis. What do we call a line that something gets close to but never reaches? An asymptote. And since this one is horizontal, we say in this case the x-axis is the horizontal asymptote. Now, what is the equation of the x-axis? You may or may not recall that, but write it in your notes. It's y equals 0. Remember, the protocol y equals b is the standard form of a horizontal line, and here our b value for the y-intercept is 0 there. So this equation is for the x-axis is y equals 0. Now as we go down, and I will keep that there as well so you can see the difference. Notice now for the positive values, whole numbers, when our a is 2 here, 2 to the x power, has this general shape, and the horizontal asymptote is still the same, but now it's in the second quadrant. Let's also, while we're here, define our domain and our range. Now this line continues on to negative infinity and continues in the right to positive infinity for actually both of these scenarios. Now how about the range? That would be the y values. Well, we said it never reaches the 0 on the y coordinate here. So it would be parenthesis 0, and this would then go to positive infinity. So this applies to both of these scenarios. Okay, background. So keeping the graphs in mind, we're talking about behavior of exponential function. Pause, read this over. Sort of a summary of what we said. Now the arrow here, the word we use for it, approaches. So x approaches infinity. So for the fractional form, it's decreasing and approaches infinity, while the increasing function is that as it approaches 0, it's increasing, which we've described. All right, let's go on. Well, if you've done some sketching already, in a sense, we've done this. We've sketched the graph of 3 to the x power and 1/2 to the x power. Or actually, I see these were reversed. So let's take a look at them. Again, I would set up a t-chart, and I'll do this one with you. So let's set up the t-chart here. And -1, 0, 1 are the points that are plotted. I've put a few more. So -1 is 1/3. So -1, 1/3. What would this point be, by the way? This would be a -2. And that would be 3 to the -2 power is the reciprocal of 2, which is 1/9. So this point here would be 1/9. This would be 1/27th, and so on, 1/81st. Again, getting closer and closer to the x-axis, but never reaching it. X-axis is the horizontal asymptote. All right, let's do the next one. Okay, take a moment to sketch this, and we'll fill these in together. So if x is a -2, we would just flip that. That would be 2 to the second, which would be 4. If x is a -1, flip that. That would be 2 to the first power is 2. And then 0, anything to the 0 power is 1. And then this is 1/2, 1/4, and 1/8. Again, I'm putting some extra points there. So if it were -2, -2 would be up 1, 3, 4 right there. So we're getting the various shape of the graphs here that we're doing, depending on whether we have a fraction or a whole number greater than 1. Again, the fractional base to a variable exponent has this shape. While if it's a whole number, remember, it generally had that shape. And one would be the opposite of the other, or the reflection. If this were 2 to the x power, that would be this line, sort of. And we would say then the y-axis is the axis of symmetry. If we were to fold these, one would be the reflection of the other. So introducing some background material as well here. All right, let's go on. Now, in looking at our next example, as in exponential functions, like any function, can be transformed in ways that results in the graph being shifted, reflected, stretched, or compressed, words that are background words. So what would happen in something like this? Function to the base of 1/2 raised to the x plus 3. What's that going to do? Well, that's going to shift it. And in case B, where we have a negative value that's raised to an exponential power, plus 1, and then here the exponent itself is negative. So rather than my sketching it, we'll use what's here, because they do a nice job, and their graph is so much better than what I could draw. So in example 1a, again, a sketch of this would be appropriate. So I bring it up a little bit more. There you go. So the red would be the standard 1/2. and then shifting it 3 units. So notice what's happened. There's the original graph. So to the left now, since we said when things are positive, it moves it in its opposite direction. So 3 units to the left, 1, 2, 3. And then here, 1, 2, 3. And then there, again, 1, 2, 3. So basically things are similar, but in shifting, notice what's happening. So again, you want to be familiar with what the exponent is, and then have this in your notes. So when you do the practice, you have something to refer to. Notice the domain and the range stay the same. Now in example B, we start off with plotting the 3 to the x power, which is our red dotted line. Now, we're going to, as a value for that base 3, it's going to be negative. So instead of this value going upwards, as we see here, starting low and going up, it's going to start at a certain level and go down, but we're also shifting it now up 1. Our y-intercept, in a sense, is going to be at 1, which shifts it actually down to the 0. 0, 0 now is our new y, and in this case, x-intercept. So look carefully at what's happening here. In fact, let me show you something here. If we had this function where it would be negative 3 as our base to the x power, you would get this kind of curve. That would be the reflection of this one, and your x-axis would be your horizontal asymptote for both of these. Of course, the domain would stay the same, but now the range would be from negative infinity up to 0. But now we're adding here a plus 1. So what would that do to this black line? Well, it's going to shift it up 1 unit. So now this is the blue line. So you get an idea of what's happening. Now in example C here, notice what we're seeing. 2 to the negative x power is actually, to make this exponent positive, we just take the reciprocal of this, or flip what we have here. This then becomes our base 1/2 to the positive x power, and we've done that graph already. Let's take a look at it. And remember, it's just the reflection of this one, which would have been, as I put it there in function notation, 2 to the x power. So 1/2 to the x power is the blue line. 2 over 1 to the x power is the red line. And we've defined earlier what the domain and range of this type of graph would be. Again, background and having good notes, and you can always go back, reflect on what we're doing. Once again, they're showing the domain and range officially down at the lower left-hand side. All right, let's go on. Now, here we want to get some background in solving elementary exponential equations. So as you might expect, this is going to lead to our further study of logarithms, which will be related to exponential functions. And here we don't have an exponent that's a nice even number. 2 to the something is not 5, so it's somewhere in there where 5 is. What value is that? But we know that 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. So we're going to use these elementary exponential equations where our values are whole numbers, or at least integers. Now, there is a protocol in solving, and rather than read this, pause, look it over, and I'll describe it in the next few slides. Okay, example 3 is in 3 parts, an A, B, and a C, and we'll do them and take some notes on it. So step 1 is to isolate the exponent on one side. So we're going to have 25 to the x power equals 125. I think you can all agree we're just transposing that negative 125 over to the other side. Now, what we want to do is to write our base so that our bases are the same. And we can see this is 5 to the second to the x power equals 5 to the third power. So we're getting our bases here so that our bases are identical. Now the next step is do this, and this is going to be 5 to the 2x equals 5 to the third. Now our bases are the same. This means our exponents equal each other. So we get 2x equals 3. X equals 3/2. So what is the value of x here? 3/2. So let's put that there and see how this works, just as sort of a check here. Now, here we have a fractional exponent that I'm going to convert to its radical form, which is 25. Now we use our denominator as our index, which would be 2. And the numerator as the power to which we're going to raise that. So the square root of 25 is 5. 5 to the third power is 125. So this checks. All right, have some notes, and we'll do another. All right, this one's a little more challenging, but let's set it up. So we have 8 to the y minus 1 power, and put that in parentheses if we'd like, equals 1/2. Now we want to get 8 here to some base where the bases are the same. Well, we know that 2 to the third power is 8, and this is going to be still y minus 1 here. Now, if we had this to a negative value, this is actually 2 to the negative 1. So now we're going to get 2. Multiplying our 3 by this, we get 3y minus 3 equals 2 to the negative 1. So our bases are the same, so the exponents should equal each other. So then we get 3y minus 3 equals negative 1. And we're going to solve for y. So we get 3y equals, transpose that, becomes a positive 3 on this side, so this is 2. So y equals 2/3. And I'll show you the check, which is down below, but that's our value for what y would be. Okay, I've looked at example 3, and as I see it here, there's 2/3. Now, if I took the square root of this, I get 3/2 to the second power. But the bases are not the same. But note, if I made this a negative 2 here, I could flip that, and I would get the same base. So let's flip this and make that a negative 2. And you'll see what's going on here. I now have bases are the same. So what is our x value? Our x value here is going to be a negative 2. Okay, now let's take a look at what the book has. And we'll just scroll through this slowly. You can pause as needed, pretty much following the protocol we've set up. And there are the answers. Now we'll go on to a practice mode in another video that accompanies this as you prepare to actually do things and then getting ready to do your certify. All right, we'll wrap this up.